So, 6 o'clock Central European Time. Hello everybody, and I wish you all a warm welcome to the GOM webinar for V8 inspection. My name is Stefan Siebold. I will be your host for the next couple of minutes, approximately 1 hour. And I have Markus Möller at my side. He's the guy who's answering your questions on the Q&A space. So if you have a question during this webinar, feel free to ask your questions using the Q&A space. We will try to answer your questions immediately or at least after this webinar to fulfill your needs and your wishes in respect to this webinar. So this webinar will also be recorded. We will put a copy of this recording on our YouTube channel so that you can review this webinar afterwards if you have missed something in between. So yeah, the topics for today, let's have a closer look on this. We want to go through a couple of topics during the next 60 minutes. One of the major topics will be the local coordinate system, which we implemented in the V8 software package. In combination with those coordinate systems, we will go a little bit into what we can do with those coordinate systems in respect to local dimensioning and also for GD&T inspections. A short overview of what we call skins, so how we handle label templates, legend templates, also report templates, and also how to configure the iInspect button to your personal needs. We have a small change in the overview explorer. I will explain what changes we have in the V8 version. A new, very powerful function will be the search function, which most of you might know from different software packages by Control F. We will go to this more in detail during the webinar. And two more topics will be, one will be the golden mesh calculation, so how to create a golden mesh out of a series of measurement data sets. And as an additional topic will be the required alignment, which will be helpful for let's say huge deviations in between a series of samples, and this will help for proper recognition of elements in our software. I don't want to go through a PowerPoint here. I want to show you all the stuff live in our software, so I will just switch to the V8 software, and as you can see, also the icons have changed a little bit for the new software version. So also the look and feel of the software on the desktop will change a little bit. So we will focus today on the GOM Inspect Professional software package, and we will go through the topics I've just mentioned. So let's start with local coordinate systems, and the first thing, or the first time you will get in contact with our local coordinate systems is already during the CAD import. So if you have a new project and you start importing CAD files, for example, CATIA files which have additional axis systems, or also UG files could have additional coordinate systems specified inside the CAD model. And if there are some, you have right now the ability to choose which of those axis systems should become the global coordinate system of our CAD model. So I've prepared the GOM part for this, so we have different local coordinate systems, and I can choose those during the import procedure to the desired local coordinate system in which I want to import the CAD model. Once we've done this, all the other coordinate systems are imported as well into the software and could be used for further inspections. So we have a couple of local coordinate systems here, which are coordinate systems on the nominal side. And as you can see inside the Explorer, these are more or less nothing else than geometry. So they have, in the end, the same behavior like planes, circles, cylinders in our software. So it is a primitive which gives you the possibility to use planes, directions, points for constructions and inspections. But this will be shown more in detail in a couple of seconds. So as it is a normal geometry, you can apply also measurement principles to local coordinate systems by using the iInspect. Let's see what is possible here. So, of course, if you just want to have a nominal coordinate system and no measurement principle, so you have no corresponding actual system, you can create a linked actual element. This will be a copy of the coordinate system in the alignment right now, and it is linked automatically to the nominal coordinate system. Or if you have already constructed a coordinate system on the actual side, you can directly link this to a specific actual coordinate system. So more or less the same possibilities you have also on planes and cylinders, for example. That's more or less the easiest thing for today. So during the import, you have the possibility to choose a coordinate system in which you want to have your CAD part, and all others are imported. And if you do not need them, of course, you can also delete those like you're doing with curves or points, which are also derived from the CAD import. Let's go a little bit more into details. So let's go to a topic, local coordinate system, and what we can do with those coordinate systems in respect of dimensioning and local dimensioning. So I have prepared here a session. So I just need an additional actual part. And when we have a look on some drawings, which I also put inside our software. So if we have a look on this, a closer look on this drawing, you can recognize that all those dimensions here, so such easy dimensions, are just starting from this point. So all those dimensions are starting or are derived from this origin. So in the next step, we want to have a closer look on this diameter, which should be calculated in a section which is underneath the origin in a depth of 20 millimeters, underneath the origin of this left-hand side circle. And I will just show you how to do this in our software. So what do we have? We have a CAD model, we have an imported coordinate system from the CAD import, which has no corresponding actual so far. I will just apply the no measuring principle for this. And we have a best fit aligned mesh data set for this. So I just switch this off to have a more clearer view. So what we should do right now is to construct a section, and therefore we can right now use, besides the original planes we already know, so the global coordinate planes, we can also choose local coordinate planes. In this case, the Z plane from the local coordinate system from import. And in respect to the drawing, we should perform a section which is 20 millimeters underneath this plane. Just select all the points, create, and everything's fine so far. I will switch this off. This section should be constructed on the actual side as well, and we need to have a circle. So this is my circle 1, and this is a fitting element on the actual side, which is in a fitting element inside the plane, inside the section we've just created. I will just make this visible as well. So we have a nominal and an actual circle, and if we zoom in a little bit, we will have also some small deviations between actual and nominal. So what you are doing normally to check those elements is to use the Inspect and to perform a check, for example, in the X direction. If you do not deal with local coordinate systems and you do not have any local coordinate systems inside your project, this drop-down menu won't be visible for you. So only if there is at least one local coordinate system, you will see this drop-down menu. And in this drop-down menu, you will are able to specify in which coordinate system you want to perform this check. So you have right now the choice between the global and the local coordinate system from import. And if you have a look on the tag here, you will just see that the nominal value will change in respect to the chosen local coordinate system. So in the global one, we are at a position of 0, and in the local one, we are at a position of plus 80. Okay. Sounds also easy. I would just perform both of those checks because I want to show you some differences in those checks and also in some further checks we will perform later on. So I will just redo the inspection of this position of the circle, in this time in the local coordinate system. This is my local or in local coordinate system from import. And let me just perform a small manual alignment. And also here you have access to the coordinate systems right now, so you can perform a matrix inside the global coordinate system or also in the local coordinate system. That is also helpful for special alignments, special manual alignments, which you might have to do. And I will just shift everything in respect to the global coordinate system, let's say by 5 millimeters to the right-hand side. And recalculate the elements. And what I want to have you look, what I want to have your attention on is these values change in the same manner, because of course the distance of the actual element is completely changing in the same way because we just have a different origin. So the orientation is the same, and it's just a different origin in between those local coordinate systems. So why do I do this? We will come to this right now. I want to show you how to derive a local coordinate system by constructing it on your own, and how to have a combination of a nominal and an actual one. So to keep this in mind, those two are only existing on the nominal side, so they have no corresponding actual element. So therefore we need the CAD model, and because I don't want to show you the Overview Explorer at this time, I use the new functionality Control F, as I've mentioned before. So you have right now a powerful search function inside the software where you can just type in to find CAD models, so you can search for categories, for element names, and even for specific keywords inside your elements. And you can also reduce this just to categories to have a less amount of hits in the drop down here. So I can just select the GOM part. It is also mentioned here on the upper place, and use the shortcut V for make it visible. So very nice tool, in my opinion, to deal without the Overview Explorer and to deal without the Explorer at all. So why did I do this? Let's have a close look on the drawing once again. I can also create this coordinate system by using those elements like this inner cylinder E and this inner cylinder F, and the plane which is described by those two planes here, to get a fully defined coordinate system. And this is what I want to show to you right now. So we have to have some 3D elements for this, and I will just go on for this. We have this inner cylinder. This will be my cylinder E. We have second one. This will be my cylinder F. And we will have a plane which is calculated on these two planes here. This is my plane D. These three elements are fitting elements. So the corresponding fitting element is, in this case, let's say Gaussian best fit element. And there we are. We have three elements which we could use to calculate a coordinate system. And this could be found in the construction menu under the entry local coordinate system, and also the old-fashioned create datum system has moved from the operations menu to this local coordinate system menu, because in the end they are not differing quite a lot. So we will go to the differences a little bit later, but they're more or less the same in our software. We will focus today on the creation by geometric elements in an upcoming webinar which is held by Hagen, which has a topic of deformation analysis. Also those orientation by orientation in 3-to-1 will be shown in this webinar, because they make more sense, or often more sense, for 6 degrees of freedom analysis in deformation analysis. This is not part of this webinar today. We will focus on dimensions right now. So let's go for the construction. So we have the possibility to choose 3 elements. So we can choose the first element. This is my plane D. We have the second element would be the cylinder E, and the third element would be the cylinder F. And what we derive from this, we can just name it by geometric elements. Nice. And what we have right now is a local coordinate system, which is coincident with this coordinate system from the import. But as we have also corresponding actual elements from the plane and from the cylinders, we can right now perform a reference construction on this, and we have a corresponding actual coordinate system. So here we are. So the difference right now is this coordinate system is just existing on the nominal side, and this is existing on both, on actual and nominal side. Why this makes a difference, I will come to this right now. So we had checked this circle towards the local coordinate system from the CAD import. And if you're not sure whether this is true, you can easily figure out if you have checked something in a local coordinate system. You will see this also in the label by this prime sign here. And even in the table here, it is mentioned in which local coordinate system the check was performed. So it is not directly mentioned in our standard result label, but you have the possibility to access the corresponding datum system here, or we'll show you a different position later on as well. But let's do an additional check of this circle to the local coordinate system, which we just created by geometric elements. And if we do this, please have a closer look on this value. So there is a small difference between the value of the check in the local coordinate system from import. I would just rename it, that is not messing you up here. So this is by geometric elements. So this has a slightly different value, and if we right now redo this manual alignment, which I've just prepared, just have a closer look on this value. If we change this alignment, the value will stay the same. What is happening here? So if I just switch this off, as you can see, even if I apply an additional alignment, let's say we will rotate this around the z-axis of the local coordinate system, this value will completely stay the same. And why this is the fact, let's have a closer look on this inside the creation parameters. So if I just go to the creation parameters of this check, some of you might have recognized during the creation of this check and the local coordinate system, which we derived from the geometric elements, suddenly this was not grayed out anymore. So in the local coordinate system from import, we did not have the possibility to access this. And what is done here is that we have a direct linking in between those two coordinate systems. So if there is a corresponding actual to a nominal coordinate system, we will use those two in combination. So we will calculate the value by taking both of them into account. And therefore, I've just prepared two small videos to clarify this a little bit. So if this linking is switched off, you are dependent from your alignment. So what is done there is you have a nominal, you have an actual information in a specific alignment, and of course they will differ a little bit whether you have an RPS alignment, for instance, or a best fit alignment. So the distance between those two inside the local coordinate system is completely different, and that's what you've seen on the GOM part as well. So if you change the alignment, so we shifted this by 5 millimeters, also the deviation was shifted by 5 millimeters. So there is a dependency in between those alignments. So yeah, we'll get a different value whether you are in an RPS or in a best fit alignment. So if you have this tick mark switched on, so with linking, you will be completely alignment independent, because what we're calculating then is that you have, once again, a local coordinate system on the nominal side and a nominal value, but you will also have a local coordinate system on the actual side and an actual value. And even if they have a different orientation towards each other, so of course, in a best fit, the local coordinate system will also be in a different place, but the relationship between the actual and the local coordinate system on the actual side stays the same. So what we are doing then is to bring those both to be coincident and calculate the distance afterwards. So right now, the distance is completely the same, independent whether you are in an RPS or in a best fit alignment. So that's a very important thing to know. So that is the reason why this value will stay always all the time the same. And these two values will change by changing the alignment. Okay, so this is the most important thing to understand, I think, if you want to deal with our local coordinate systems in a proper way. Let's go back to the drawing. As you can also see in the second page, we have right now the distances mentioned in a, let's say, twisted or rotated coordinate system, which is not any longer calculated by D, E, and F, but by D, E, and H. And we have also a position check of the same circle here in this datum system, D, E, and H. And that's the next thing I want to show to you right now. So I will just redo the construction. Right now we will use different elements. So I will have to have my plane D. And by the way, you can just drag and drop those elements by marking them inside the Overview Explorer and just drag them into the 3D. So you can completely make them visible by just drag and dropping them inside the software. So what is missing is the cylinder H, which would be the outer cylinder of this O. And sorry, I want to name it H. So that was just F2. I think all of you know this. This is a fitting element. And I will just switch off this local coordinate system so that this becomes a little bit clearer. Okay, once again, construct local coordinate system by geometric elements. And right now we will choose first element D, second will be E, and the third will be H. And what you will receive is a slightly rotated coordinate system. And I will just hide those to make it a little bit more visible for you. And perhaps also hiding these elements. Right now, what we are trying to do is we have a rotated coordinate system towards the global one, but the orientation of the directions is as similar as the global one. So in an automatic orientation mode, you can see this here, you will have an orientation with as less as possible rotation and translation to the global coordinate system. If you do not agree to this orientation and you want to orientate the coordinate system in a different way, you can just choose the orientation mode to a manual mode, and what you will receive then is that you will have two directions. One is identified by this circle, and one is identified by the square, and the positive direction of both is indicated by these spikes here. And right now you can choose in which direction those elements or those directions should look, and therefore you can completely define your own orientation of those local coordinate systems. So once you've found your proper orientation, so I want to have this one looking into plus y and this one into z direction, so that the positive x coordinate is going in this coordinate system. Once you have chosen the correct orientation, you can just apply the create button. But I want to show you one important additional information on local coordinate systems, and this is the default calculation method. So you can also change the computation method inside the creation command to GD&T mathematics. So this will be completely equal to the calculation method we are using to define datum systems. So as we are supposed to perform a position check to this datum system, I would just switch this to the computation mode GD&T. And here we are. We have a local coordinate system on the nominal side, and I would just bring this with reference construction on the actual side. So I will just delete those first checks. I just want to have it a little bit clearer. Hope everybody of you got this, that there are two different calculation methods, so by geometry and by GD&T. I will go to this topic a little bit later, once again. I've mentioned that you can recognize the datum system in which it was checked using the table. And I want to show you a different position where you can find the information on this, and therefore I just want to have, let's say, a second check onto this circle. And as you've seen, I've used the shortcut by using the control button to overcome the creation parameters, and it is automatically then choosing the proper local coordinate system for the second check. So once you have performed a check in a local coordinate system to an element, the next checks would make sense to do the same checks in the same local coordinate system. So we have two checks, but if we have a look on the drawing, we don't want to have it checked to this local coordinate system by geometric elements, which we created first. We want to have it to this coordinate system right now. So we did a small mistake, and we want to change this right now afterwards. So how do we do this? You can just highlight those by using control button inside the label and just select those two checks and open the properties button so that you have the properties information. And here you have also the information in which coordinate system these checks were performed. And also the using of the linking of the actual and nominal is accessible here. So you can change easily the coordinate system here by just highlighting them in 3D and just changing the coordinate system. As you can see right now, the values have changed. So, as I've mentioned before, in the drawing, we should perform a position check towards this coordinate system. And because we have already said that the calculation should be for the GD&T mathematics, we can also use this local coordinate system for a position check. So I can just use a position. I don't have to create a datum system because we have already the coordinate system, which is nothing else than a fully defined datum system in the end. So I can choose this local coordinate system by geometric elements. And here we are. We have a position check, but on the drawing it was mentioned to have not a planar, a circular inspection type, and right now it is also a little bit easier to recognize in which directions those checks are performed right now. So formerly we had these 1, 2, and 3 direction up, down in this drop-down menu. Right now you have a proper mapping of the directions in respect to the local coordinate system. So we have to perform the check in the X and Y plane, so you can easily recognize which direction you should use right now. So that's it. So what is the advantage of this approach is right now you can have the GD&T check, which is first mentioned on the drawing, but you can apply in addition some local dimension checks so that you can give more information to your customers or to your colleagues. So what do you have to change to get a better value for this position check? Because the position check in the end is nothing more than whether it is good or not. So this gives you also additional information in which direction you have to correct something. So that's it for coordinate systems and for checks on this side. I would just give you a small hint where it might also be useful in drawing-based inspections. So of course you can also check distances. So if you have a 2-point distance in between the origin and the circle, also reference construction, and you want to check this distance in the x direction, also here you could choose the local coordinate systems. So you can also choose a local coordinate system, the proper coordinate system for this local check. So, and once you've done this, of course, you can also do this in the y direction. And once you've done this, you can also use those visualizations to have a more or less look and feel of a drawing in the end. So you have also the possibility to just check locally x and y distances and of course positions as well. Okay, so that's the most important stuff for the local coordinate systems. Let's have a closer look on the last page. I just want to mention once again the difference between local coordinate systems and datum systems in this case. If we have a look on this, we have a position check to a datum system which has a transformation left in its degrees of freedom. So it is not completely defined. So it is not a completely defined coordinate system, and therefore we still have to use our create datum system method, which those guys of you which already dealt with GD&T tolerances might have known under operations. As I've mentioned, this is already implemented in V8 under the local coordinate system menu. So what we have to do right now is, once again, I need my cat. I need to have a plane. Let me just create those. So I have plane A and a plane G. This is my plane G, and I have to have the plane for my inspection. Those three are all fitting elements. And our GD&T approach is independent from the method you are using here in calculating a corresponding actual element. We are using only the selection inside the datum system creation. So right now the software is not using the calculated geometry, but is using the selection for the geometry and is calculating in respect to GD&T mathematics, so Chebyshev mathematics, the proper datum A and the proper datum AG in this case. So the default behavior for datum system is the GD&T computation. I've mentioned this before on the local coordinate system. There the default behavior is the geometry. So you can either choose whether you want to go to geometry or to GD&T mathematics on both sides, so on local coordinate systems and on datum systems. But the default behavior is different for those two elements. This is important to know if you want to do such things as I've shown you before. So if you want to perform position checks and give additional information in local checks in X and Y, for example. Okay, here we are. So if you have a non-complete local coordinate system like this A and G, you still have to use the create datum system method. For complete coordinate systems, you can choose whether you want to calculate a local coordinate system right now. Let me just do the position, and I can also show you some small side effects on this. If I choose the A and G, even right now in those datum system check dialogues, we have a corresponding direction with a nice mapping that, let's say, an X prime and Z prime. So the Z prime and the X prime direction, so you can easily recognize in which direction you want to perform your check right now. So this is a nice side effect also coming out of the local coordinate system calculation. Okay, so this is a little bit heavy stuff, but it is very powerful for improving the section drawing-based inspection capabilities of the V8 software right now. So we have implemented these local coordinate systems for several reasons. One is, of course, the dimensioning of local coordinates. Others are on deformation sites for 6 degrees of freedom analyzers. So this is part of the next webinar. So feel free to join this webinar as well if you are interested in some more capabilities on local coordinate systems. Right now, I want to show you one last thing, because I guess we have a lot of guys on the plane industries here taking place in or joining us here in the webinar. Those coordinate systems could also be used for, let's say, a little bit advanced alignments. So if we are talking about blade alignments, you might recognize that we have, in this case, a blade which has not the same orientation, or which has a local coordinate system, which should be used for an alignment as well. So this is not corresponding to the global one. And if we have a look on the alignment, this will be an RPS alignment, and I will just make the actual elements visible as well. So we have on this side some touching elements which are already checked in a local coordinate system, and we have also symmetry points which should have an influence in a local direction. Right now you are able to perform an RPS alignment in a different coordinate system than the global one. So let's just do this. So I will just use these elements, put them into the proper dialog. So let's say this was Y, this was Y direction, this was the Z coordinate, and this should have an influence on the Y coordinate. As you can see, right now we are dealing with the global coordinate system. You can see this a little bit in when you have a closer look on the angles between the directions and the portion the alignment should have in this direction, and also on these touching points, they have an influence in X and Y right now. I'll just show you the difference. So looks not so bad. So everything's gone to 0 except this symmetry point here. And if we perform the same RPS alignment, but adding an additional constraint, and here we are in the in the more advanced stuff. So you can choose a general constraint which allows the to choose a local coordinate system. And if we do this, you can also already see inside the dialog that we are right now using the X and Y and Z prime directions, and also the angles are now much better. And therefore we are able to have a proper alignment for such specific alignments, or even for tool alignments which are not in the same orientation as the global coordinate system. So if we switch back and forth, you will see a slightly different orientation, but as we all know, those guys from our plane industries are cheating the microns. So this is also an improvement which is coming with the local coordinate system. But right now, I've said we have, let's say, an hour to go. In the end, we have already 45 minutes done. So let's have a look on different topics today. So I've mentioned require alignment in the first step. And I want to show you right now what is meant by this. For those guys of the injection molding industry or casting industries, they might have to deal with, let's say, huge deviations in between sample part 1 and sample part 2 towards the CAD file in the end. So you might have huge deviations, and you want to have a stable recognition of elements in this case. And this might have been a problem in V7 from time to time, or it was at least tricky to have a stable calculation on this. So let's create just a small plane here and apply a measurement principle here as a fitting. And as you can see, in this orientation, so in this alignment, in this pre-alignment, we are not able to calculate a proper actual plane due to the fact that all these points which should lead to a plane are too far away from the actual data set. So right now you were a little bit messed up. We have implemented a new functionality for this. So if we have a look on the properties for this actual plane, you will see in the parameters here that the fitting elements and also other elements require an alignment for its calculation, and afterwards they are just transformed from in between the different alignments. In this case, the pre-alignment is not good enough to have a proper calculation of the plane, but we can change this. So let's just perform a local best fit. So let's do something like this. So we have a local area where we can stably orientate the M towards the CAD file. And if we go to the edit creation once again and just apply OK, right now we have changed the needed alignment for its calculation. So right now the plane 1 should always be calculated in the local best fit 1. And even if I now switch back to the pre-alignment, also in the pre-alignment, right now this plane is properly calculated. And to show this a little bit more in detail, I would just pop in a second mesh. Could be a replacement if you have a second part, or it could be a new part for a new stage evaluation, so a series evaluation. So we do not make any difference between a trend session and a normal session inside V8 anymore. So every single G-inspect file could be a stage file or a single inspection. So I just apply a second stage for this. I will have to recalculate everything, and you will see that even, where's my, there's my stage. Sorry. I will have to just recalculate the alignments for the stage. And if I now switch back and forth, you can see even if we have huge deviations in between part 1 and part 2, the plane 1 is stably found right now. So small improvement, but it might be very helpful if you have to deal with some huge deviations between part 1 and part 2. Another thing which was mainly driven by our customers, so from you in the end, is the question why you are not supporting run out and total run out. This is not the fact anymore, so we have implemented this in V8, so we have filled the gap in GD&T. So we are right now able to calculate total run out and run out checks. So have a look on this. So we have a datum which doesn't make sense in terms of of the part itself, but it's nice to show you right now. We have two cylinders here, a cone and a cylinder on the top. All of them are fitting elements, and right now I can just check the cylinder. For instance, there's a total run out in respect to this cylinder, and if we have only one datum, so we do not have the need to create a datum system beforehand, so we can just use the element itself. And we are also right now just using the selection of the actual elements and calculate a proper datum system out of the selection in respect to the ISO definitions. So we can calculate a run out, a total run out on this, and we can perform a run out on this cone in respect to the datum system K. And I will just zoom in a little bit to clarify how we calculate this. So I will switch this off. So let me just increase the tolerance a little bit, so you can see that in the total run out we have a tolerance zone which is two coincident cylinders which have the same, or which are coincident with the datum. And on the other side, the run out right now, this is a little bit more tricky. We have, I have to choose this first. If I increase this, you will see that we have slices of cones which have the distance in between as a tolerance zone. So that's a new small improvement on the G&T side, and this brings me to one additional small improvement, but also nice. Some of you might know that we are able to visualize the deviation also in terms of a color deviation plot. So we can visualize also GD&T checks like flatness or surface profiles in terms of a GD&T of a color map. And what I want to show to you right now is that you can just adjust for every single color plot one specific legend. So this was not possible, so, or was not easily possible in the V7. So right now I want to have, let's say, plus minus 50 microns for the cone, and I want to have plus minus 0.1 for the run out color plot. And as you can see, when I switch them on and off, the legend is completely knowing which element is displayed right now. and is adjusting the proper legend which you have just chosen for this. This leads, of course, to the fact that if you're displaying two at the same time, which have different legends, we have to do something. So in this case, we won't show any color unless you just change it to a common tolerance zone, or if you just hide one so that there is one legend which represents all the color information which is displayed in the 3D view. Also small but nice improvement, I think, for dealing with legends and color plots. So, one last but not least, I just mentioned that we have changed also something which we call skins. So the handling of label templates and report templates, legend templates, and we had also some report templates for this. All this stuff is not handled inside several or in specific styles. It is always, or it's all in combination, is handled with a new functionality which is called skins, and this could be found underneath here and in the lower left corner. So you have a drop-down menu here, and we have prepared two standard skins for deformation and inspection analysis, and I will show you what the difference is and how you can deal with this to customize the look and feel of your iInspect, and also the look and feel of the label styles and so on. So just a short hint. So I have let's say a circle here, and I want to have the result label, so this might make something more clear to you. Sorry, I want to have the result check. If you have a look on the iInspect, and if I change right now the deformation to the deformation skin, you will see that the GD&T alignment or the GD&T functionality is not displayed anymore inside the iInspect. And if you have a look on the offered checks, this is also not any longer a distance X and distance Y. It is a displacement. So because you have different approaches for different inspection tasks, so you need also different checks more often. So that's more or less the major need for having such skins. If we want to investigate deformation analysis and inspection analysis in the same software, we have to deal a little bit with this to customize the software to our needs. What else can we do with this? Some of you might think, yes, you have the GOM makes nice labels, but I just want to have the diameter always on top of the X, Y, and Z check, and I don't want to have the DN on top. I want to have it on the bottom, and I don't want to name it DN. It should have the name normal. So you want to customize your labels, and this could be done also by using these skins and in combination of this configure iInspect, which is to be found in the inspection configure iInspect. And here you are able right now to customize the look and feel and the behavior of the iInspect, and also from tables and checks. So you can, as I've said before, I want to have the diameter not always on the bottom of this result label. I want to have it on top. So you can just move it upwards to a top level, and you can also choose the normal inspection to have it always underneath the X, Y, and Z orientation. You can switch on and off things, and also you can change the name in the end of the of the check. So right now you see the diameter check is right now always on top of this result label, and the formerly known DN is right now mentioned normal. So you can completely customize your eye inspect in the look and feel. You can even switch on and off checks. So if you don't want to have the radius anymore and you don't want to have the in plane or X and Y and D, and also no GD&T or blade functionalities, right now also the look and feel of the check dialog has changed. So first X, then DN, and no diameter anymore. So you can completely adjust this to your needs. Once you've done this, you will see this by this small marker here. You can manage those skins and you can save them, export them, and reuse them on different PCs in the end. So it is stored inside the GInspect file. So once you have changed something inside inside your inspection, it is also transported with the GInspect file. So your colleagues have the same look and feel then. So I just choose this, and if I switch back to the inspection, you can also see that also the order of those labels is reordered then. Also, small and nice improvement, I think. I have also shown some smaller improvements on the Overview Explorer. So we have a lot of categories in addition, so you can see what is imported, what was created in a specific datum system, and you can drag and drop those elements, and by holding the shift button, you can also show them exclusively. So you can drag and drop those elements in addition. So you see this, there's a small plus sign at the mouse. So you can add those, or you can just show them exclusively. In combination with the Control F function, you can also make the CAD model visible for this, and so you can easily deal with the elements itself. Yeah, that's more or less the small changes inside the Overview Explorer. So you have a Overview Explorer. Down here you have a list of all selected elements inside the 3D. So also this behavior changed a little bit. And you can manage whether you want to have an auto expand of the Overview Explorer up here, or if you just want to leave it the way it is. So play a little bit with this. I think this is also a small improvement in V8 to deal with a lot of information in this case. So, because I'm already late, I want to switch to the last topic for today. So there's also a new functionality which is called Golden Mesh. And what we can do here is, if we have, for example, a sample of 4, in this case 5 different measurements. So if you have a closer look on the meshes, I hope you can all see that there are some small deviations towards the single samples. There's a new functionality implemented on the operations CAD, so in the CAD menu, to create a golden mesh. And there you have 2 possibilities. So you have the possibility to find a best mesh. This will just find one of those 5 samples to be the best one, so to have the least deviation towards the others. Or you can create an average mesh out of these samples here. So create an average mesh. It is doing a little bit more than just finding the best mesh. It is actually also finding automatically a best mesh, but then is using the vertices in respect to this reference mesh as an averaging of all those sample data sets which are taken into account. So there is a small difference. So an average mesh is a really new calculated mesh, and find a best mesh, this is just to find the best sample out of a series. This could be exported as STL, G3D, or just make it as a CAD for further inspections. Yes, in the end, 1 hour and 5 minutes. So I didn't make it in 60 minutes. I'm sorry for this, but finally, we went through all of these topics. I hope you enjoyed the last 60 minutes, and I hope I could tell you some new improvements in V8. And once again, this webinar was recorded, so we will put a copy of the recording on our YouTube channel. And also, you will find in the support area, in the download area for the GOM V8, which will be released at the end of the week right now, you will find the proper download for the software packages, and also the procedure how to update your dongles and your licenses on your dongle. And you will also find there a document which is called What's New, where you will also find the description of local coordinate systems, which we went through this webinar today, and a lot of more information and a lot of more improvements which we implemented in V8. And that's all from my side. We will stay a little bit tuned on the Q&A space, so if you have questions, feel free to ask. Yeah, hope you enjoyed it, and hope you will join our next webinars as well. Next one will be in the next week, on also same time, same place. I guess the topic is deformation analysis, and we have also a VMR webinar coming up, so feel free to join those. Yeah, that's all from our side, so have a nice day, and yeah, we'll see each other, and bye.